Thank you, everyone, for joining the workshop. It's a pleasure to be part of the IRIS National Spectrum proposal. Today, I'll talk about spectrum issues for terahertz, which is what we've been working on as part of IRIS. Today, I'll briefly talk about what's above 100 gigahertz, because that's where I've been leading our efforts across many universities. How much spectrum exists, I think you'll all be surprised, and I think Andrea is going to be relieved that Wi-Fi will have a safe harbor in these great bands above 100 gigahertz. I'll talk about some fundamental research in spectrum management that we believe IRIS could bring to the national stage and help the US keep its early lead that I'll talk about. And then I'll talk about some of the IRIS study project that we've been doing as part of the planning grant with our original NSF work at 140 gigahertz, looking at some foundational new approaches that we never thought about in spectrum. And finally, I'll be delighted to introduce you to the students and show a live demo of how they've conducted this pilot study. And then I'm going to talk about something that I believe is very important and that IRIS is going to look at, and that is health effects, how we can lead the nation in understanding if there are biological effects. So since I'm talking about terahertz, I just want to clarify that terahertz technically is above 300 gigahertz, which is only a few orders of magnitude below the visible optical spectrum. The visible optical spectrum is at 430 terahertz. And so we're talking about 1 to 3 terahertz, which is just really only 2 orders of magnitude below that. Ionizing radiation, where the energy is high enough to break electrons out of the valence shell, occurs above optical, up in the ultraviolet X-ray and gamma ray area. So we're still 3 orders below ionizing radiation, but we're moving to a regime which is really not well understood. Now, the FCC helped launch this interest in terahertz, and for this talk, I'm going to just say that terahertz is above 100 gigahertz. So I'm not being a purist at 300 gigahertz, but I'm going to show you the next generations of wireless are going to go well above 300 gigahertz for all the work we're doing in 5G. But the FCC opened up this excitement to the terahertz world when they proposed their Spectrum Horizons docket in 2019, which opened up these 4 new unlicensed bands that you can see on the right, opening up several gigahertz of spectrum available today for commercialization. And for the first time ever, the FCC made rules that go above 95 gigahertz all the way up to the 3 terahertz spectrum range. Now, what's fascinating about these frequencies is at the same time the FCC was opening up the spectrum above 100 gigahertz, and I had the good fortune to be presenting them with a lot of work that we were doing at the time. At the same time that was happening, there was this very big public debate that some of you may have noticed. It was the NOAA weather satellites concerned about the FCC's move to open up the 5G spectrum down at 24 and 28 gigahertz. And what the issue was is that the passive satellites, which fly above the Earth in low Earth or medium Earth orbit, were trying to measure very accurately the signals looking from above Earth down to the atmosphere to measure water molecules. This is how we do weather reporting. I've given you a lot of really valuable links. And this was a big debate because there was worried about out-of-band interference, out-of-band emissions from the 24 gigahertz cellular 5G efforts, how they might leak into these very, very passive, very, very weak signal detectors that are in the passive satellites. This is also an issue for radio astronomy, where they're using these very, very directional sensitive telescopes that Marwan was showing in his last talk, and trying to resolve deep space signals that are literally hundreds, 120, 150, 180 dB weaker than interfering signals. So it seemed like there needed to be a national arbiter, or at least a place where objective science and engineering could be used. We believe IRIS could be the center that can help bring experts together in the community and help US agencies quantify these issues. Just to get an idea of how divergent the views were from 2 of our important government agencies, namely FCC, which governs the commercial spectrum, and NTIA, which governs the government spectrum, you can see these 2 different views in the popular press. Fortunately, this was all resolved at the ITU stage, but it shows the importance of having good technical engineering and physics to help solve what will be an ongoing debate, as I show you shortly, in these much higher frequencies. Just to give you an idea of how sensitive these passive sensors are, they're measuring just a few degrees Kelvin. They're using basically cryogenically cooled in space receivers with wide open front ends, trying to find very weak signals. So they need to be protected. And in fact, we held an expert meeting as part of our IRIS Center, which I think may have been the first meeting of its kind that brought national experts from both the US and around the world to study the issues surrounding what might happen with co-channel interference and out-of-band emissions. We had radio astronomers, wireless communication experts, policy experts, and it was a remarkable, very candid 4-hour meeting where we learned the great sensitivities of the passive sensor community and the radio astronomy committee. There were experts from CORF, the Committee of Radio Frequency, which is part of the National Academies. And we had a really good candid debate when we started on this IRIS proposal center. And that debate has really impacted not just our proposal, but it's actually had international ramifications. I'll show you in a minute. But that debate produced some key facts that we must protect the passive bands. No ifs, ands, or buts. These tiny frequencies where there's resonance of atoms and particular elements coming deep from space must be protected, just like these passive sensors orbiting above Earth. Out-of-band emissions are going to be key above 100 gigahertz as we evolve these future consumer spectrum uses. And radio astronomy told us in this expert meeting that they would really love to have access to the commercial bands. That is, there's a lot of deep space science that could be done if there could be certain times scheduled where radio astronomers could look into the frequency bands and detect things in deep space, something that the wireless community's never thought about before. And Marwan, with his colleagues, Chris Walker and Allison Ford, helped bring this to the fore in our IRIS Center. And then finally, the idea of spectrum auctions, even though you don't think 100 gigahertz or above is popular, but it will be, as I'll show you shortly. In the next 20 years, it will be as popular as today's 6 gigahertz spectrum. And there could be spectrum auctions, and the proceeds from those auctions could provide huge amounts of dollars that could go in to support radio astronomy as we bring together these communities of passive users and the commercial world. So there could be a dividend for future R&D in astronomy funded by wireless telecom. Now, let me show you why I say that things are going to work well above 100 gigahertz. This is a really important graphic my students put together based on ITU knowledge. People don't think this way, but if you look to the left, the attenuation in dB per kilometer is in orders of magnitude. If you look at dry sea level, we go all the way out to 800 and 900 gigahertz, where there's virtually no additional attenuation due to the atmosphere. And even with moistures at standard sea level, look at the blue curve. The blue curve all the way out to 800, 900 gigahertz, we're only having 10 dB per kilometer of loss. So the idea that things are very, very lossy all the way up to 800 gigahertz really is not true. There's virtually no loss compared to down at 0 gigahertz in terms of added loss due to atmosphere. But that's when you're on Earth. That's really astounding. And so all the peace dividends of 5G with the amplifiers and phased arrays and packaging, they're all going to carry to 6G and 7G, all the way up to hundreds and hundreds of gigahertz. Secondly, the amazing thing about radio propagation is on Earth, the rain rates really flatten at 100 gigahertz, actually about 50 gigahertz. So as we make 5G millimeter wave wireless and Wi-Fi work for small cells and rural several kilometer cells at millimeter wave with huge bandwidths, the rain is not going to impair frequencies up to hundreds of gigahertz any more than it does now. That's a remarkable result. Now, here's the amazing thing when you start to think not just on the ground, but looking at satellites. If you look at the graph on the right, you'll see that we have free space path loss out to hundreds of kilometers at 140 gigahertz. Technically, it's only 160 dB of path loss. That is technically, with directional antennas, We can go up to 140 gigahertz and beyond with very little attenuation loss. But when you go up into space and start considering what ground-based transmitters will do for interference up to these passive sensors, you see that the atmosphere and even rain starts providing hundreds of dB loss. That is to say, just like in today's cellular, where the indoor-outdoor barrier helps protect the outdoor cellular network from the indoor cellular and Wi-Fi network, future terahertz wireless communications on Earth will have the atmosphere to provide a natural barrier from radiating out into space. This is important to realize that these path losses are hundreds of decibels, 10 to the 30. We're talking huge amounts of natural attenuation from Earth up to space. Nevertheless, we've learned from the astronomy community and the passive sensor community that there can be no room for error as these astronomers look for these very weak signals, these elements at different frequencies. So even though there's this natural barrier, it's still important that we protect these passive bands. But I just want to make clear this wonderful natural attenuation that exists due to the troposphere as we go to about 10 to 20 kilometers above Earth. In fact, my students plotted this graph on the right, and you can see 1,000 dB path loss for various low Earth orbiting satellites. So as we go above Earth, or if we have UAVs or high altitude platforms, we'll have to consider this kind of loss. Now, I said how this SII proposal from the NSF has generated a lot of national and international conversation. One of the places we've seen it is in the Millimeter Wave Coalition. The Millimeter Wave Coalition is a nonprofit group of major companies from around the world and a few universities. NYU is the first academic member. And this plot was just produced this week for this talk by the Millimeter Wave Coalition. Kudos to Joseph Jornet and Mike Marcus, colleagues in the Millimeter Wave Coalition, and Joseph students for creating it. This shows the wild, wonderful landscape above 100 gigahertz. What you can see in these vertical gray bands, these vertical gray bands are the prohibited bands. These are protected bands that radio astronomy, passive sensors, NTIA in the US, globally, there's agreement that no one will operate any wireless terrestrial networks in these vertical bands. These are prohibited bands for any communications of any type. And that's where various molecules, oxygen, hydrogen, where people like Chris and Allison and the radio astronomers are looking for deep space phenomena to find the quasars, to find the exploding stars, the redshifts in these bands. They would love to go out of those bands on occasion as wireless consumer use grows. The green on this slide shows all of the allocated co-primary fixed and mobile around the world. Huge amounts of spectrum are waiting for the mobile industry. And this is why the National Center for Spectrum, IRIS, needs to be able to provide basic knowledge and policy and understanding of these frequency bands. Now, the FCC got out in front of the world with that Spectrum Horizons ruling I told you about when they allocated, for the world's first time, these 4 blue bands. These 4 blue bands are the unlicensed bands that exist today. And England followed very quickly. About a year later, Ofcom opened up these same Wi-Fi bands. So we see the emergence of new global Wi-Fi bands in these ranges. In the blue bands, they'll likely build out around the world. The important thing to see here, though, is on these curves show at a 407 kilometer length how much path loss attenuation there is in these spectral bands. And you can see that there's natural attenuation in some of these bands, but still all the way up to 260 gigahertz down at the ground, the low curve, there's virtually no huge attenuation on this length. So the point is, and also these numbers at the top show the number of passive satellites that we could deduce from FCC filings that are existing in these bands where there are sensors orbiting the Earth. So we have to protect these. And the question becomes, how close can we get to these protected bands with terrestrial networks without interfering? That is, without providing out-of-band emissions. That's a real big research issue as we explore the bands. Now, what will 6G and millimeter wave and terahertz bring us all kinds of wonderful applications. We heard Mate talk about them in his keynote. But one of the things he mentioned was position location, and that is very exciting. Future terahertz and millimeter will have built-in position location capabilities. In fact, think of the Snapdragon DSP in the Qualcomm smartphones today. These basebands have computing power that 30 years ago took rooms and rooms of computer to do. I remember in 1990, I did ray tracing with a room full of Spark 2 Sun Micro stations, workstations, and now you can put that in a phone. A cell phone will be able to do real-time ray tracing and be able to use knowledge of the multipath coming from the adaptive antennas and the wideband time dilation and the time delays in the received signals, and we'll be able to predict on the fly position location very accurately. This is an approach we've developed at NYU using ray tracing and knowledge of the environment. And look at these amazing results with just one base station. We can get within 30 centimeters, 40 centimeters, over 126 meters with a single base station. We can do it for drones, we can do it for base stations, and in fact, going up to 140 gigahertz with just a single base station and using extended common filtering with a map built in the phone or downloaded from an edge server, you can get very, very accurate position locations, really remarkable, on the order of 29 centimeters over 34 locations. These are actual measurements. So position location indeed is going to be coming to the wireless world as we go up to these higher frequencies. Now, part of our planning grant in the SII effort as part of IRIS was to do a great deal of work at 142 gigahertz. And I want to thank Nada for her wonderful keynote saying how important it is that databases be made available. At NYU, we've always published all of our data. We've given technical reports and path loss values all throughout our measurement campaigns since 10 years ago when we started looking at millimeter wave. We're going to do the same thing at 142 gigahertz. But we were making all these outdoor measurements for microcell, small cell when the SII initiative came along, and we realized studying satellites was really vital to see how much ground energy can bounce up to a satellite or to a tall base station, which is being used just for backhaul. And then we want to take that data and put it into channel models. So what we did is we were making measurements all over the New York campus. Some of this is not published yet, but it's fascinating. So during COVID, we've been measuring the campus very carefully. This is Brooklyn, New York. So it's a microcell urban environment, 10,000 power delay profiles. Look on the right, you can see the rooftop receiver that's emulating a passive satellite, base stations on the ground, rotatable antennas, horn antennas, because we don't have phased arrays at 140 gigahertz yet. But this is all at 140 gigahertz. And we've been measuring for the last year, producing raw data that's informing us. On the left, you can see the satellite looking down on Earth. Actually, it's just on a roof. But the idea is, what would a satellite see? And what we've been studying is how these environmental factors work at 140 gigahertz. And we'll be going up to several hundred gigahertz. This is vital knowledge that IRIS will produce for the industry and also for the federal agencies. What's amazing is this. For outdoor mobile, 142 gigahertz is virtually the same as today's 5G. I'll say that again. Propagation in non-line of sight and line of sight at 140 gigahertz is virtually identical to 5G's 28 gigahertz. The only difference being the path loss in the first meter. The path loss in the first meter, we're in the far field at 140 gigahertz, dissipates the wave. So what that means is we just need more directional antennas to overcome that first meter path loss to make up the link margin, and all the work we've done for 5G will carry on to above 100 gigahertz. That's great news. The second interesting thing we did as part of IRIS is we put that rooftop location on the left, and we went to various places on campus to see what what a base station or a mobile user on the ground would do if we could keep the radiation on the ground, or if it bounced off buildings and went up to that surrogate satellite on the right. And what you can see is if the transmitter on the ground has a little tilt up towards the sky, things will bounce, not very many. It's very hard to find it, but you could very rarely find multipath that if the antenna elevation on the ground was above the horizon, energy could be caught by the roof. This is a very busy slide. It's brand new data, but look at the blue curve and the red curve. These are, if you could keep terrestrial transmitters at 0 degrees horizon and 8-degree horizon, the received power at a passive satellite is 40 dB down below what theoretical free space would be. This is great news, not just for satellites, but also for future millimeter wave backhaul. It means that if we can build antennas on every mobile that stay on the horizon, energy will not get up to a higher elevation where something could be interfered with. And remember, this is before you apply hundreds of dB of additional loss up to the satellite. So what this means is if we can build mobiles of the future with antennas on the horizon, the patterns on the horizon, there will be no interference up to the backhaul superhighways in Earth and up to space. So before I turn it over to the students to give a great demo, I just want to end this part of the talk before I talk about health effects with a fundamental principle that the world still doesn't get, but they're learning. This is how the world thinks of millimeter wave and terahertz today. They think of the graph on the right. They think that path loss goes higher as you go higher in frequency, right? Everyone says you don't get more coverage because it's lossier at higher frequencies, but it's quite the opposite. This curve on the left shows that thinking is wrong. The old thinking, this thinking, is when you assume an omnidirectional antenna. When the gains are removed, it assumes an omnidirectional antenna at both ends of the links. Quite the opposite though. In this case, you can see blue 140 gigahertz has higher received power. When you use the same physical size of the antenna at the transmitter and receiver, you get more gain as you go higher in frequency. So if the antenna stays the same physical size at the transmitter and the receiver, you get more power, not less power. That is, you get free additional gain in the channel, which gives us bandwidth for free. Phenomenal result. And with that, I'm going to turn it over to the Spectrum pioneers who are working on behalf of IRIS to show you how we did all these measurements and what we plan to continue to do. Over to you, team.
Hello, everyone. My name is Yunchou Xing. Welcome to the lecture of the Wireless Propagation Lab at NYU Wireless, which is part of the IRIS Spectrum Research Center. First, I want to introduce our third generation channel sounder working in the sub-terahertz band at 140 gigahertz. Previously, we have conducted measurements in the millimeter wave bands at 28 and 73 gigahertz, and we have characterized the wireless channels at millimeter wave and proved that millimeter wave could be used for 5G communications. Now we have moved to the sub-terahertz band at 140 gigahertz. Here is our channel sounder system. This card contains the baseband components of the transmitter and the control systems. And the arc hider is put on a gimbal, which can rotate 360 degrees in the azimuth and 120 degrees in the elevation. The transmitter radiates out the signal through a high-gain horn antenna, and the signals pass through the wireless channel and will be captured at the receiver. Let's go to have a look what is happening at the receiver. Here is the GUI of our receiver channel sounder system. You can see the red line is the real-time power level of the captured signals. If we record one measurement, and one power delay profile will be recorded and contains all the information we need for the measurement. Let's do a quick demo. If a person is passing through the link between the transmitter and the receiver, you can see a human blockage introduce some loss in the power level. In addition to the human blockage, we also measured and modeled reflections, scattering, and penetration at both millimeter wave and sub-terahertz frequencies. Based on all the measurements we conducted and the data we collected, we have developed statistical channel model and implement the statistical channel model into a simulator, NYOSIM. Next, I will ask my friend Ojas to introduce NYOSIM.
Hi everyone, I'm Ojas Kanheri and I'll introduce NYOSIM. NYOSIM is an open source millimeter wave channel simulator that can be used to simulate various channel properties. Over here, this is a user interface on which you can set the environment of operation, the frequency which can go all the way up to 150 gigahertz. This depicts the output that NYUSIM generates. And the good thing about NYUSIM is that it's for free. We've done extensive measurements indoors and outdoors and collected a vast amount of data. And all this data is then modeled into a channel model. And this data output over here can be directly used by researchers to do various simulations. There's angular information over here, channel impulse response, path loss. All this can be used by researchers. And if you have any problems with NYUSIM, you can always contact us by email, and our lead developer, Shihao Zhu, will help you.
Thank you, Ultras, for the introduction of NYOSIM. So could you also please introduce some of other research you are doing?
Of course, I'd like to introduce an application of millimeter wave and sub-terahertz, position, location, or localization. This horn antenna over here operates at 142 gigahertz, and it has a narrow half-power beamwidth of just 8 degrees. Similarly, phase arrays operating at these frequencies will have very narrow half-power beamwidths. This allows very accurate estimation of angle of arrival. And because of the wide bandwidths at these frequencies, you can have very accurate estimation of time of flight as well. These two combinations lead to very accurate estimation of position location. You get centimeter level position location accuracy. And this opens up a wide variety of applications such as AR, VR in gaming, factory automation, and navigation in locations where the GPS signal is denied.
Wow, centimeter level precision location.
That's right.
That is amazing. Thank you, Ultras. Let's go to my friend Deepankar and see what is happening here.
Hello everyone, my name is Deepankar Shakya and I will be talking to you about the miniaturization of the channel sounder system. Moments ago, my colleagues showcased a wonderfully sophisticated and large channel sounding system. Now we are working to integrate multiple components of that channel sounder system into miniature integrated circuits such as this one, which will be available to the industry and academia for very low cost compared to the actual channel sounding system. And we are placing these chips onto test circuits, which we are conducting various tests on in different lab conditions. In the future, we envision the form factor of the channel sounder become very compact and portable so that industry and researchers can conduct channel sounding at frequencies above 100 gigahertz.
So you are talking about you are going to miniaturize this big channel sounder into a small box?
Yes, both the TX and RX into the same transceiver system. Now, because we're working with RF signals, that we definitely need antennas to radiate that energy out into space. So we are working on phased antenna arrays that can accurately direct the signal into space without interfering into frequency bands of other systems that coexist in the spectrum. Now I would like to talk to you about the RF probe station environment at NYU Wireless, which can measure up to 220 gigahertz. And for the demo, I've placed a single patch antenna that is a few hundred micrometers in dimensions, as can be seen in this zoomed in picture. And the probe station is feeding in different frequency signals into the antenna to characterize the antenna's response at its operational frequencies.
So Deepankar, you are talking about you are going to make phased arrays at frequency of 180 gigahertz.
Yes, 180 and several hundred gigahertz in the future.
Thank you, Deepankar. Thanks for the introduction.
Thanks, Joe, and thanks everyone for tuning in. Live from the NYU Wireless Research Center as part of the Iris Spectrum Research Center. It's been a pleasure having you. Back to you, Professor Rappaport.
All right, that was great, and that was live. So now I'm going to go back to this and from the current slide. Okay, so I'm at the end of my time, but these are really the pioneers, and this is what NSF is allowing us to do to create the future leaders that are going to pave the way to this new frontier, the frontier above 100 gigahertz. Thanks to all of you for that live demo. Now, I mentioned health effects, and I'm at the end of my talk, but I just want to show you that we really don't know much above 100 gigahertz, but as we wrote in our position paper on 6G and above a couple years ago, this is a personal passion of mine. And I think any National Spectrum Center must responsibly study what potential health effects exist. Now at NYU Wireless, we've worked with the med school for 5G and we're doing it for above 100 gigahertz. We believe right now that everything's known that heating is the only thing that matters. But given these recent guidelines by the Non-Ionizing Commission, it's important to understand what heating might exist for future wireless devices for mobile and fixed. It's important for the public to know. And also, it's important to understand how to measure that best. And so we can use MRI in a very sophisticated way to determine heating. We've been doing that. We published a paper on it in 2015, and we're actually looking now to do this at above 100 gigahertz, where we can measure temperature from a phantom. And we've already done it at 24 gigahertz, trying to understand how wearable appliances are. So this is really an important issue. And if it's not just heating, a center needs to be able to look at what might be the effects on animals. So at NYU, we have at the med school the capabilities to study mouses and rats and to look at long-term exposure. These are important kinds of things, and the industrial affiliates of NYU Wireless have been behind this SII proposal, the IRIS Center. And with that, I'll just conclude to say, no one would have thought 10 years ago that millimeter wave would ever be worked on. I was kind of scoffed at when I gave talks 10 years ago about the millimeter wave future. And now we see 5G rolling out around the world, and the Apple 12 smartphone has millimeter wave in it. Well, we're going to do the same thing above 100 gigahertz, and the US needs to lead. We have the early lead above 95 gigahertz. You should be convinced that there's clear sailing well beyond 700 gigahertz from this talk. We have to protect the astronomers, the passives. IRIS can do it. With that, thank you very much. I'll turn it back over to Gina.